All right, let's do it. All right, so hello everyone. My name is Stannard. I am the CEO and founder of Petabridge. We're a company that helps .NET developers build highly available distributed systems. The biggest thing that we work on is Akka.net, so I'm one of the co-founders of that project. And today, I'm going to be talking a little bit about how it's supposed to work. And we had a really significant problem. Around the time we released Akka.net, I think it was 1.05, back around October of last year, someone made a very subtle change in the way our serialization system worked, and it more than halved our throughput. And this was the difference between some of our customers' apps being able to stay up and available, and some of them going down because things were getting backed up inside the system. So the performance really did have a significant impact on how our customers' users experience their software. And one of the really major problems that we had when we were trying to figure out what the real underlying performance issue was quantifying it. How quick is Akka.Remote? What sort of throughput can it deliver with what size message and under what circumstances? And here's where I got really frustrated, watching our contributors try to figure this out. Every single one wrote their own little benchmarks that had completely different instrumentation, completely different warm-up and sort of setup periods. And so everyone was trying to talk authoritatively about how fast Akka.Remote worked, using completely different standards and completely different measures. The idea behind a benchmark is you have a single bench and a single mark on it, just like in woodworking. If everyone has their own bench and their own mark, it's useless. It's like watching ferrets describe how a supernova works. So, in order to try to make a workable solution to this problem, I came up with a system that we could integrate into our continuous integration process, where every pull request would produce metrics around how well Akka.Remote worked. And what you're seeing here, this plot, are all of the pull requests from December 1st, 2015 through March 21st, 2016. So this is where we began. This is the low performance period here. And this number reflects the number of messages per second over a single Akka.Remote connection. So we're hovering somewhere around like 2,400 messages per second, which is bad. It's pitiful. Well, the first change we made was we found a really simple way we could eliminate some string formatting functions used by our logging system. If you weren't using that logging setting in production, which most of our customers weren't, we didn't need to go through the overhead of formatting that string, which actually ended up being really expensive. So we got this jump here. And then we got another jump in productivity when we found a statement where someone was fully evaluating a data structure instead of lazily evaluating it. So we're paying this big tax every single time, even though we didn't need to. Now here's something interesting. This giant jump in performance here is because I screwed up our benchmark when I was refactoring it one day. So this isn't a valid number, but because I can correlate this data point in time with a given pull request, because of the way our build history system works, I can prove this number jumped up for an invalid reason. We can have that conversation as a team now and basically discuss the performance of Akka.Remote with data. Now this big dip right here, all the way back down to it, was when I fixed our benchmark, and at the same time, this is right around New Year's, the license that our Windows Azure Community Edition Visual Studio boxes expired, and I had to completely re-image all the hardware our build system runs on. So we sort of lost our hardware profile we were using here and had to start from scratch here. And then we had a couple of other incremental changes sort of over time here, and you can see the performance is gradually improving. Now, the most important part of this graph isn't the fact that we improved the performance significantly, it's the fact that the performance never dropped again after we started measuring it. There's a saying in entrepreneurship when you're talking about sales and marketing metrics, which is that if you can't measure it, you can't control it. The same is true for your performance. If you can't measure how quickly something runs, or how much memory it uses, or how much time it takes to do something, you can't have an effective conversation with your team about how well things work. So this is the story of how we used NBench, the technology I'm about to show you, to solve a real problem that was causing significant issues for our users. I think of performance testing as a type of defensive programming. And what you're preventing against are small changes that might seem trivial, but actually have a very profound impact on how quickly or how well your application runs. So, good example, memory consumption. How many of you today are doing mobile application development? Quick show of hands. All right, so I'd say about a quarter of the room or so. On a mobile device, memory is at a premium. It's not like server-side programming where we can run our software on machines that have 64 or 128 or 256 gigs of RAM. You have to go ahead and put a premium on memory when you're developing your application to run on someone's cell phone. Total throughput. This is what the server-side folks worry about all the time. We've got to make sure that we can turn around as many of our customers' requests as possible. Garbage collection overhead. The number one cause of speed and throughput issues in most managed languages is going to be the garbage collector. It's particularly if you have, we'll talk about the different generations of garbage collection in .NET in a moment, but if you have a lot of Gen 2 garbage collection and you're not using the server GC setting, this can cause a pause across all your threads every 20 to 30 milliseconds. I/O is another issue. If you make a change to the way a piece of code works inside your server-side application, and all of a sudden that increases the number of round trips you have to make to your database, to the file system, to an external API call on the network, you want to measure that. Because I/O is another form of bandwidth that you have to conserve in order to stay performant. Number of network calls, same idea. And then shared resource contention. This is a particularly tricky issue. The idea is that if you have multiple asynchronous or concurrent processes all trying to access the same resource, you need to measure how high the contention overhead is on that piece of code. Because that's going to be a source of overhead that can gradually creep up on you over time. So another quick show of hands. How many people in this room have suffered from SQL Server lock contention overhead? Look at that across the room. It's virtually everybody. So this is a real problem too. One of the things we have to do in order to sort of get a grip on performance and start treating it like a first-class feature in our applications is we have to have some measure of lifecycle management for it. So the way I recommend doing this is the first thing we need to think about are the performance constraints of our system. So the mobile developers in the room, you have very different performance constraints than I do as a back-end developer. You have to worry about the amount of cell phone bandwidth that you consume on your end user's application. If you use up a ton of their bandwidth and give them an overage, they'll uninstall your app. And you also have to worry about things like memory utilization and CPU too. On the server side, we might have to worry about things like throughput and the total amount of execution time, that sort of thing. Next thing you need to do is identify the performance critical path for different areas in your application. If you have a little startup function that only gets run once, that may or may not be on the performance critical path until it is. Until maybe someone changes it where now all of a sudden it takes 20 seconds instead of a few milliseconds to start your application. Then you set targets. These are the marks we put on the bench. What are some of the numbers that we want to achieve? So for instance, in Akka.NET, we have a goal of being able to fit n number of actors into 1 gig of memory. So we want to make sure, okay, can we fit 1 million actors into a gig or 2 million actors? It doesn't really necessarily matter what the initial target is. It just gives you something to work towards when you're starting to work on improving the performance of your application. Then you measure how well you do against the target. So if we want to get 2 million actors in memory, which means that each actor by default has about 500K of sort of memory footprint, but we need to figure out if we're above or below that target right now. So if it turns out every actor uses 800K in memory, then we know we have to find some areas to make our actors less fat. And then lastly, you have to update the performance history. Performance isn't a dot, it's a line over time, like the graph I gave you. One of the things you have to do is maintain a history of how the performance of different parts of your system evolved over time. If you only go ahead and run a benchmark manually, for instance, every time you feel like it, and you don't run it on every single build, you might miss a really critical change that got merged into your code base that really degraded some performance in your application. So having a regular practice of updating your performance history is essential. And it's essential for mostly human reasons, not for any technical reason. Like I mentioned earlier, the first problem we had when we found this performance issue with Akka.Remote was that no one could have a coherent conversation about it because we were all using our own benches and marks to do it. Having a single source of truth performance history, and I'll talk a little bit about how to do that in a moment, but having that enables your developers to actually participate in the conversation with the correct information. So you don't have people with 10 different benchmarks that all report totally different things. So this is probably the most important part of the entire performance lifecycle. Yeah, and then you go ahead and feed in the regular updates here. Yep. And yeah, if you go ahead and do a major update of your software, you basically have to go and redo all this all over again. So if you go from like a version 1 to a version 2 of your software, you might have to go ahead and pick totally new performance constraints. Now, where NBench, the technology I'm going to introduce, we fit in this realm right here. A profiling tool, like if any of you have used .trace, it's one of JetBrains' product, or any of the built-in Visual Studio tools, those are something that you'd use more along here, per se. NBench fits into this part. We're designed to help you measure all of the incremental performance changes that occur as you submit patches to your software. So performance testing is hard. Some of the reasons why we had those conversations where no one could be on the same page about how Akka.Remote performed is because you have to factor in things like operating system unpredictability. In particular, if you're performance testing concurrent code, you can't predict necessarily how the operating system will schedule that work. There could be lots of different possible interleavings that get scheduled on every single run of your benchmark. Next is virtual memory. If you end up running a benchmark that goes and uses a fairly large amount of memory, some of that will start getting paged to disk using the virtual memory system every operating system has. And that'll go and show up in your benchmark in a fairly dramatic way. So we have to factor this into our consideration for when we design the hardware we're going to use for benchmarking and the actual benchmarks themselves. And lastly, other processes. One of the NBench specs that I'm going to show you failed this morning because I was running another set of NBench tests on the same machine, both using the same operating system and the same hardware, and that had side effects there, and you can't avoid that necessarily. Next thing is hardware variability. So one example of a subtle problem that we've had in the Akka.NET project is we actually use TeamCity with Windows Azure agents that get spawned on demand. And even though all those agents supposedly run the same hardware profile according to what we paid for on the Windows Azure portal, truth of the matter is there's actually a lot of variations in how that hardware works. So we might see one instance of a benchmark on the same type of virtual machine produce a consistently different result than another. And that's due to small variations in how the hardware works, even within one Azure data center. And yeah, so there's all sorts of like CPU level hardware variations you have to worry about. Runtime and dependencies. So when we start thinking about the different parts of our application, something as subtle as the version of the JIT that you're using might have a big impact on its performance. Or maybe the GC settings you have enabled. If you turn on server-side GC in an NBench test, all of your memory tests are going to get totally thrown off, because the way we actually measure memory is based on what the garbage collector is tracking. And so that setting there really goes and changes that a lot. And lastly, down at the bottom, a lot of developers, despite us being sort of mostly left-brained sort of people, aren't nearly as good at math as we think most of the time. So having a consistent way of going and instrumenting and computing the values of a test is important. If someone's taking a look at a percentile versus an absolute number versus an average, none of those values are going to look the same, and they might mean different things. So you have to have some standardization around how you gather the metrics from the underlying system to begin with and how you instrument those. Yep. And then actually difficult to design the isolated tests themselves. Some of the things you have to worry about when writing a benchmark is you have to go ahead and force a GC collection between each iteration, and you've got to worry about other forms of background noise. And The good news is NBench does all that for you. So you don't have to worry about a lot of that yourself. The idea behind NBench and why we developed it is that it's meant to basically feel like writing a unit test. Unit testing is something that, a quick show of hands in the room, who here has written a unit test before? Okay, everybody. Everyone knows intuitively sort of what it means to unit test. And that wasn't true 10 years ago, by the way. So what I decided to do with NBench was, because I have to support a team of contributors for Akka.net, it can't just be me writing all of it. I decided, we need to come up with a look and feel that's familiar. And I think unit testing was the best analog I could come up with. We also write all of our output to files. That makes it very easy to build a performance history, as you actually get hard output that you can compare over time. All of the data is reliable and believable. We do all sorts of reliability tests inside NBench to guarantee that certain mechanisms for collecting data work as expected and as advertised. And NBench is fast. One of the things that's kind of ironic about a benchmarking framework is it typically has to be faster than the thing it's benchmarking. So I had to do a lot of work to make sure that was true. NBench is also configurable. You can go ahead and tune lots of different metrics it can collect and specify how many times you want to run a particular benchmark, how you want to set it up, etc. And it's extensible. People have been able to go and write their own little plugins on top of NBench, and they've been able to integrate it with other technologies. Like there's some folks who use NBench with XUnit theories to go ahead and write assertions, that sort of thing. So these are the sort of basic ideas behind NBench. And it's OSS. It's all licensed under Apache 2, and it's completely free as in beer. Now, let me go ahead and give you a little demo of what an NBench test actually looks like. If I pull up, look at the Akka.net project here real quick. So this should count for your Akka.net checkbox on the bingo card. There you go. All right. So this is a basic NBench test here. What we're testing for, as the name implies, this is testing how much actor memory we allocate when we're testing different types of actor implementations in Akka.net. So you don't need to worry about this. This is the actor we're testing. This is the other actor we're testing. Here you go. So the first thing that we're going to do is we have this little setup method right here. This gets called before each run of the benchmark. And we're going to pass in this little benchmark context object. And what this gives us access to are counters that NBench allocates. Counters are used for measuring throughput of different parts of the system. And one big difference between NBench and a couple of other benchmarking tools out there is NBench is designed to benchmark asynchronous and concurrent code. That's what Akka.net is. So all of our counters are inherently thread safe. So a good practice for any benchmark, what I'm doing here, is I go ahead and I allocate my actor system, which I need to create the actors whose memory I'm going to manage, and I allocate my counter before the benchmark runs. I don't want any of that data throwing off the numbers for what I'm going to intend to measure later. Then down below here, I have a little method that I decorate with a perf benchmark attribute. And I go ahead and provide a little description. I say that I want to run this as an iteration benchmark. There's a couple of different types of benchmarks out there. There's iterations and throughput. Iterations is what you would use if you have a piece of code that's reasonably complex, and you just want to run it multiple times. Whereas a throughput function is used for like micro benchmarking, very small pieces of code. I'm going to run it 13 times. You want to use prime numbers for computing the iterations of your computer. That way you can avoid any of the even number optimization stuff a Intel chip might try to do. And the test mode we're going to use here is called a measurement. This means we're just going to measure the data from this benchmark without performing any assertions against it. If I wanted to turn this into an assertion, I can go ahead and say we're going to run assertions. Let's see. And I could go ahead and change one of these properties here. So these two properties are different types of measurements we're going to do on this benchmark. One is going to measure the throughput. How quickly do we create actors? The other is going to measure the memory. What are the total bytes allocated for this block? Now, in general, if you want to measure the amount of memory a particular object takes, the best way to do that, and this is somewhat coarse-grained, but this is what I found to be sort of works best for us, allocate a lot of them in one fell swoop, and basically take the average of that. There's going to be some things the operating system and the CLR does, like they'll go ahead and allocate memory for your application in pages, which are usually 8K long. Actually, I think it can depend sometimes, but they're going to allocate memory in pages. So you might want to allocate enough objects where the page size doesn't become relevant anymore. So in this case, I think I'm going to allocate 10,000 actors. That should be enough for an accurate test. And one of the things I can do here is I have this memory measurement attribute. I can replace that with a memory assertion if I want. So we'll go ahead and call it memory assertion. The memory metric will be total bytes allocated. And I'll say must be, we'll go ahead and say greater than or equal to. And I can go ahead and say, I think I have a byte constants. Here we go. 32K. So 10,000 actors must be able to fit into 32K. This assertion will fail. Actors are a bit bigger than 2K each. But this is an example of an assertion we can do. Now, this is sort of a basic benchmark. We can do some more sophisticated things with NBench if we want to, such as, let me go ahead and pull up an example here from Helios. Here we go. This is Helios. This is the socket server that powers Akka.Remote under the hood, and it's a separate project. What we're doing right here, so we're measuring a bunch of different metrics. You can see I'm keeping track of a few different counters. I'm measuring garbage collection across all generations, and I'm also measuring total memory. This is what we call a stress test. Doing a performance test of a single unit of code is still a good practice. Allows you to measure how well a particular unit works. But measuring how well a bunch of features running together at the same time works is also necessary. It's kind of like the idea of an integration test versus a unit test. What we're doing here with this particular test is we're calling it, it's a stress test. I'm going to try to open as many clients and basically as many client sockets as I can connected to one server and see how long I can go until the amount of time it takes to allocate a particular client exceeds some predefined threshold I created. So I won't bore you with the details on how that benchmark's implemented, but I will show you what the output looks like. So the output you get from NBench by default is a markdown file that looks like this, and I used a Sublime Text to render it into a web page. So I can see my description here, I can see some of the information about the underlying system, and I can also see what the NBench settings were. Then if I scroll down, I can see the totals that NBench produced for all these different metrics. So right here, these metrics at the top, these are the total number of garbage collection attempts per generation that the CLR produced. So you can see here, I have a fairly high number of Gen 0 collections. That's good. Gen 0 is the fastest. That means that those objects were allocated and collected within local scope. Gen 1, I have a little bit more of those. And then I have some Gen 2 collections here, and we'll talk a little bit about more of those in a moment. Then I can see the total number of inbound and outbound operations. So we can see it's about 22.5 million total operations across the board here. Then total number of connected clients. So I was able to connect just under 850 socket clients to this server on my machine here. And the test could have kept going, actually. I watched this one run. But that was how much that we sort of decided to try within this given period of time. Now the next thing you'll see, those were the total values. You can also see per second totals here. So this scales relative to how long the test took to run. So you can see that I have an average of about 2 Gen 2 garbage collection attempts per second under this model. Now, is that something to worry about for this particular test? The answer is no. We're doing something that you typically wouldn't see in a production application, which is spinning up a ridiculous number of clients on one machine connecting to itself. Typically, that would happen over the network. And so the garbage collection semantics would be a bit different there. But if I went ahead and made some changes to Helios down the road, and that number jumped up significantly, that means that a lot more of the objects I allocate are being passed to an outer scope and are being retained by something, which might mean I have a potential memory leak, or I'm allocating a lot more objects than I used to. And that's something that our team would investigate if it came up and showed up as significantly different in one pull request. And then down below here, You can see that the total system throughput for reads and writes is roughly about the same, 85,000 messages per second. This isn't a true throughput test, so our actual throughput on a socket is actually much higher than this. But this goes to show that we're maintaining, despite this increasing load on the system, a relatively even parity between inbound and outbound writes. That means that we didn't screw up our implementation on one half of the way the socket library works. Then you can see I'm averaging roughly 3 connections per second here. This is a test that ran for several minutes. It allocated a huge number of connections at the very beginning and began to slow down gradually as the system got busier and busier and busier. Then if I want to take a look at even more detail, I have raw data for each run. Now this stress test only really ran once, so let me show you a slightly different benchmark. This is testing inside Helios, the same socket library, the underlying kernel that we use for executing all the events that percolate up on the socket itself. If I take a look through here, I can see that this executor is able to execute on average 4.7 million operations per second, and it has a maximum value of 6.7 and a minimum value of 3.1 million. That's a pretty huge divergence, isn't it? That's a big range of possible values. Why could that be? The answer was I was running all my Akka.NET benchmarks I was going to show you at the exact same time as this. So the CPU was busy under the hood. And as a result, you get big divergence here. So let me close out, there we go, by talking a little bit about performance best practices. First thing you want to do is make sure you integrate your benchmarking directly with your build process. Your build server should be the source of truth behind the performance of your application. Anytime a developer uses their local machine to try to compare a benchmark that was produced on another machine, the conversation should just end and you should just run it on the build server. Both of you are wasting your time. Next, run all official benchmarks on the same hardware. Hardware divergence matters when you're benchmarking. You can't disregard it. So that's why we recommend integrating this with your continuous integration process. That way it's your build agents that are always computing the official values of record. Yep, and always under the same conditions. Don't do what I did this morning and run my benchmark while I have something else going on the machine at the same time. The other is reset your baseline performance whenever your dependencies change. If I upgraded from .NET 4.5 to .NET Core, I need to reset all of our benchmarks because .NET Core has a fundamentally different way of how it's implemented some of the constructs I depend on. I have to include that in our numbers now. Yep, so hardware is one dependency. The underlying operating system is another. If you upgrade from one version of Linux to another, or one version of Windows to another, you need to reset your baseline there. And if the runtime changes, like .NET Core. The other thing is always save the NBench output somewhere. One of the things we do in all of our open source projects, let me pull up a browser here. You see here, this is the set of performance tests that we run on every single pull request. I can dig into any one of these. So this is like the latest development branch. I can see all the different output we've generated for every single performance benchmark that we've run. And I can compare that to any other branch that I want. Or I can compare that to previous versions of the dev branch. And this gives me a clear picture of how any given metric we measure has changed over time. So if you're interested in learning a bit more about NBench, I strongly recommend that you go to the repo here. Pull this up. I recommend that you go to the NBench repo and play around with it. One of the big things that we're working on adding in the near future is a JetBrains ReSharper plugin, so you can go ahead and run your benchmarks directly from Visual Studio. But today we have a bunch of command line tools for running it and getting output reports. So on that note, thank you very much, and have a good rest of the conference. Thank you.